Right now, you can't remember being 1 year old. You couldn't even a week after you turned 5, probably. But at 1 year old, you were doing incredible things. You were learning to walk. You were starting to say your first words. You already recognized your parents' faces, their voices, their smell. None of that made it into your memory. Here's the actual mystery. That period of your life was the fastest learning your brain will ever do. More new skills, more new information, in less time than at any other point in your entire existence. And almost none of it left a trace you can access today. Scientists have a name for this gap: infantile amnesia. And for over a century, the leading theory was simple: babies just can't form memories yet. The hardware wasn't ready. In 2025, a team at Yale and Columbia ran an experiment that broke that assumption completely. They put infants, some as young as 4 months, some as old as 2 years, into an MRI scanner, awake, which is its own small miracle if you've ever tried to keep a baby still for anything. They showed each baby a series of new images. Later, they showed the same babies a familiar image next to a brand new one and tracked which one the baby looked at longer. Babies tend to stare longer at something they recognize. That's the whole test. And here's what they found. In babies older than about 1 year, the hippocampus, the brain region responsible for forming memories, lit up during the first viewing. The stronger that activity, the longer the baby later stared at the familiar image. In other words, the baby's brain was encoding the memory in real time, and you could watch it happen. So, the memories are being made. The question just got harder, not easier. If the memory gets encoded, why can't you retrieve it as an adult? To understand that, you have to understand what memory actually requires. Not just one step, but 3. First, encoding, turning an experience into a pattern of brain activity. Second, storage, holding that pattern somewhere over time. Third, retrieval, being able to pull that pattern back up later, on demand. Most people assume infantile amnesia is a failure of step 1. The Yale study suggests it might actually be a failure of step 3. The memory gets made. It might even get stored. It just never gets handed back to you. So what's actually happening inside a baby's brain that would cause that specific kind of failure? 2 things happening at the same time, both dramatic. The hippocampus itself is still physically immature at this age. It's not just smaller, it's still wiring itself, cell by cell, connection by connection. Meanwhile, the rest of the brain is doing something almost unbelievable. It's producing new synapses, the connections between brain cells, at a rate it will never match again. By some estimates, an infant's brain forms roughly 1 million new neural connections every single second during peak periods of early development. That's not a typo. 1 million a second. Now think about what that means for anything stored during that window. Every new connection has the potential to reroute, overwrite, or bury the pathways that were holding an older memory in place. Neuroscientist Paul Franklin has a related theory. New neurons are still being born in the hippocampus at a rapid rate during infancy. Each new neuron that gets wired in can disrupt the existing circuits, including the ones holding older memories together. It's less like a filing cabinet losing pages. It's more like a construction site that never stops rebuilding its own foundation. So are those early memories actually gone? Or are they just buried under the construction? This is where it gets stranger, because the answer might depend on which animal you ask. In mice, researchers can do something we obviously can't do with human infants. They can go in and directly manipulate the neurons themselves. In several experiments, young mice learned a task and then, as expected, appeared to completely forget it as they grew older. Adult mice, tested normally, showed no sign the memory had ever existed. But when researchers used a technique called optogenetics to directly reactivate the exact brain cells that had encoded that original memory, the mice suddenly responded as if they remembered. The behavior came back. That's an extraordinary result. It suggests the memory was never actually deleted. It was sitting there, intact, just disconnected from the normal pathway you'd use to reach it. A separate study in rats found something just as strange. Memories formed during the rat equivalent of infancy seemed to vanish completely. But if the rats were given a small reminder cue later in life, related to the original experience, the full memory came roaring back, in detail, as if it had never faded at all. The researchers called this a latent memory trace. Present, but silent, waiting for the right key. Nobody has found that same reactivation key in humans yet. But it's the reason some scientists, including one of the Yale researchers, have started entertaining what they call a radical, almost science fiction possibility. That some of your own earliest memories might still physically exist inside your brain right now. Just permanently locked, with no key that works. There's a second, completely different piece of this puzzle, and it has nothing to do with neurons. It's language. Look at when infantile amnesia actually ends. For most people, it's not a clean cutoff. It fades out gradually, somewhere between ages 3 and 7, and that window overlaps almost exactly with a huge shift in how children talk about their own lives. Researchers who study this have identified specific verbal milestones. The age a child first uses past tense to describe something that happened to them. The age they start narrating their own day, unprompted, the way adults do. Long-term studies tracking the same children over years have found that hitting these language milestones predicts which memories survive into later childhood, and which ones don't. Before you have the words for yesterday, before, or I remember when, it may be genuinely difficult to build a memory in the narrative shape your adult brain expects to find later. Not because the experience didn't happen, but because it was never encoded as a story. A story needs a beginning, a middle, and you as the narrator. You didn't have the language to build that story yet. Once you can say I fell down at the park yesterday, you're not just describing a memory. You're building the exact shape a memory needs to survive. Now, a word of caution here. Because this same research area contains one of the most famous cautionary tales in all of psychology. In the 1990s, researcher Elizabeth Loftus ran an experiment called Lost in the Mall. Researchers told adult subjects a false story about getting lost in a shopping mall as a child, an event that had never actually happened. A striking number of participants didn't just believe it, they started producing vivid, detailed memories of the event, complete with sensory details. A more recent replication found similar results, with roughly a third of participants developing a false childhood memory of an event that was entirely fabricated. This matters for our story specifically. The years right before your accessible memory begins are a fragile window. Your brain, during that window, is unusually willing to accept a memory that isn't real. All it takes is someone else supplying it convincingly enough. So even if scientists eventually find a way to unlock those early memories, there's no guarantee that what surfaces would be the truth, rather than something reconstructed, borrowed, or entirely invented. Which brings us to the actual question underneath all of this. Why would evolution build a brain that works this way at all? Why sacrifice years of episodic memory, right when the brain is doing its most extraordinary learning? The leading idea isn't that infantile amnesia is a flaw. It's that it might be the price of something else your brain needs more urgently. In that first year or two, you're not just collecting individual memories. You're building the underlying machinery, language, motor control, facial recognition, an entire framework for understanding cause and effect. Some researchers argue the brain is making a trade. Specific episodic memories traded away. General, reusable knowledge kept instead. The kind of learning that has to stay flexible, not locked to one specific afternoon. Under that view, forgetting isn't a bug in the system. It's what clears space for a brain that's still actively building its own foundation. And that theory is still just that, a theory. Nobody has definitively proven why this particular trade-off exists, or why humans experience it more severely than most other species. Here's where the science actually stands today. We know infant brains encode memories. We know, in animals at least, some of those memories can be forcibly reactivated later, which suggests they're stored rather than destroyed. We know language plays a real role in which memories eventually become permanent and retrievable. And we know the years where this is all happening are also the years where a memory is easiest to distort or fabricate entirely. What we don't know is the part that would actually solve the mystery. Whether there's a real key sitting somewhere in the human brain that could unlock those very first years, or whether, for humans, that door is simply closed for good.